Hello, everyone. Good morning, good afternoon, good night. It's my pleasure to start one more webinar on our GLASE Webinar Series. Today, we're going to be talking about humidity control in greenhouses and other indoor plant environments. The GLASE Consortium Webinar Series is a selection of live recorded online presentations that cover a broad range of topics at varying technical levels and scale. These webinars feature the latest technological innovations and best practices in the CEA field, providing the audience the opportunity to discover new solutions and to connect with field experts. I would like to introduce today's presenter, Dr. Nadia Saba from Dr. Greenhouse. Dr. Saba, also known as the Dr. Greenhouse, is president and founder of Dr. Greenhouse, an agricultural and mechanical engineering firm that is specialized in designing HVAC systems for indoor plant environments. Dr. Saba first became interested in controlled environmental agriculture as an undergrad while working on a small coffee and oyster mushroom farm in southern Idaho. For over 20 years, Dr. Saba has dedicated her education career to helping farmers control their environments, allowing them to grow crops indoor in greenhouses and locations that would otherwise make it impossible or impractical to do so. She and her team have designed HVAC systems for facilities growing cannabis, strawberry, leafy greens, vine crops, and mushrooms all over the world, including Europe, the Middle East, Canada, and the US. Dr. Saba has her PhD in agricultural engineering from University of Arizona's Controlled Environmental Agriculture Center, also known as CEA, and is licensed mechanical engineer in the state of California. She currently serves as a chair of the ASHREA, a SHIRE, co-sponsor committee responsible for developing the standards HVAC for indoor plant environments without sunlight, serves on HVAC advisory committee for Resources Innovation Institute, and is actively engaged in academic and industry research. A recorded version of this webinar will be available at our website, glaze.org, afterwards. So you can come back and revisit this video at any time. If you have any questions about the presentation or would like to get in contact with the speaker, please submit your inquiries using the chat box. So we have a Q&A chat box, and you can also get in contact with email by me at any time. We will do our best to answer all your questions at the end of the presentation. So now, without taking any more time, I would like to turn the word to Dr. Nadia Saba. Saba, it's a pleasure to have you here today and look forward for your presentation.
Thanks, Erico. Really appreciate the invitation to talk about humidity control. I know that this is a challenge for a lot of indoor growers and greenhouse growers, and I'm happy to share my experience and my expertise on the subject. As I was developing this, I was telling Erico that as I was developing this, I was thinking, how am I going to talk for 45 minutes or an hour about humidity control? And it turns out that there's a lot to talk about. Maybe nobody else is surprised. So I have a lot of content. I'm going to be moving fairly quickly because I know that there will be questions at the end, and I want you to be able to ask those. So quick overview. These are the basic topics that I'm going to present here. First, I want to start with what is humidity and where does it come from? Why do we want to control humidity? And then how can we control humidity? And why the heck is it so hard to do? So before we begin, I'd like to ask you to please fill out this poll. I'd like to have a better understanding of who our audience is today. So if you can please check one of these boxes, give you 30 seconds or so to make your decision on who you are. Then we can see.
All right, folks, 15 more seconds. We're almost there. We have 70 responses out of 97 participants. Getting there. I'll close the poll in 3, 2, 1. All right, done, because we have a second one coming up. There you go, Nadia. So you have most of your participants are greenhouse growers. That's excellent.
Awesome. What's most? What's the percentage? I don't see that on my
We
screen.
have 32% of our attendees are greenhouse growers.
Okay.
Then we have 28% indoor growers. 24% are academic and researchers. 15% are service providers. 17 other, and 5% lighting manufacturers. To give an idea, the number one, which is 32% greenhouse growers, we have 26
Got it.
people
Awesome.
here. I'm sharing the results.
Ah, there it is.
I should have done that, sorry. My second time using polling. I know better the next time.
Fantastic.
Everyone can see, and then we have, great, and we have a perfect, there you go.
Okay, and then you want to pull up the second poll. The second poll is asking about what crop or what crop you're growing, or maybe are researching or are interested in learning how to control humidity for. Let's put it that way.
There you go. Second one is live. Everyone can get that back to us.
And if it's, I guess we could, Erica, we could have had a topic, we could have had a selection of more than one or multiple. Maybe you could pick more than
multiple choice.
This is a multiple choice, you guys. So if there's more than, if you're growing hemp and leafy greens, check both boxes.
Exactly. All right, guys, 10 more seconds. We have more people answering question number 2 than number 1. I think that's a good sign. Yeah. Almost done. All right, let me end the poll, and now I know that I can share the results. There you go. So leafy greens is the winner here.
All right. Well, good. I'm glad. I'm going to basically be talking about all of these in one way or another. Okay.
Wonderful. All right, let's get going. Thanks, Nadia, for taking the time.
Absolutely. Thank you guys for taking the time so that I can get to know you a little bit better. I'll say if everyone was growing lettuce and basil, then I, might not talk about cannabis too much. All right. So moving on. All right. What is humidity? Okay. So humidity in general terms is the amount of water vapor in the air. This is a very generic term that just gets thrown around, but there are so many different names and parameters associated with humidity, trying to quantify this water vapor thing, right? Okay, so we have absolute humidity, also called the humidity ratio, and this is the absolute quantity of water vapor in the air. Okay, and it's usually on a mass per mass basis. Relative humidity, which is probably the term used most often in the industry, is the ratio of water vapor in the air versus the maximum amount of water vapor for a given temperature. It's a ratio, right? That's why we see it as a percentage. The vapor pressure deficit is kind of the same thing. Now it's the difference in water vapor in the air versus the maximum possible. So relative humidity is the ratio, and vapor pressure deficit is the difference of the same exact variables. So the reason we call it relative humidity is because it all depends on what the temperature is. We can have the same exact absolute humidity, the same exact quantity of water vapor in the air at 2 different temperatures, and our relative humidity sensor will read 2 different relative humidity percentages. Okay, so as the temperature increases, basically we get a glass that is larger and the relative humidity goes down. But we could have the same quantity of water, say this glass, but it's a smaller glass. It's a lower temperature air. It can hold less moisture, and therefore we get a higher relative humidity. So if you look at these two middle glasses, this one on the left would be, say, 60 degrees, and this one on the right could be 80 degrees, and we would get a different relative humidity, but the same quantity of moisture. That's why it can be very confusing to talk in terms of relative humidity. On the other hand, vapor pressure deficit is an absolute difference. So we know how much water is in the air versus how much there could be. For horticulture, for agriculture, plants really respond to this difference, to this vapor pressure potential or difference between what's in the air versus what's at the leaf. And usually at the leaf, we consider that the saturation vapor pressure. The water is saturated. It's still in its liquid form when the water, pushes out of the stomata. And depending on what the vapor pressure is in the air, that's what's going to drive transpiration. So if we looked at a psychrometric chart, we could say, okay, we're in a greenhouse at 80 degrees and 60% relative humidity, and this is where we would be on the chart. Okay, this would be your relative humidity. And over here, we could go all the way over here on the right side of the chart. So I'm throwing a psychrometric chart at all of you. Maybe some of you are familiar. And we read what the vapor pressure is. Now, if we go up this chart all the way to the top at the same exact temperature, this is our temperature, okay? And we go all the way to the top, this is the saturation curve. The difference between the vapor pressure here and the vapor pressure here is the vapor pressure deficit. Now, I'm going to come back to that in a second. Now, other important humidity parameters that all of us should be aware of is, one, wet bulb temperature. This is the theoretical temperature at which air can be cooled to saturation when we add water vapor to it, okay? This is the process of evaporative cooling. The dew point temperature is the temperature at which water condenses out of the air. So those of you who have greenhouses, say in Ohio or another cold climate, when it's really cold outside, the surface of your greenhouse cover gets cold. But you're holding a condition of, say, 80 and 70% relative humidity inside, and that water now condenses on the cold cover, and that's why you get dew forming on the cover of your greenhouse. Now, like I mentioned before, vapor pressure deficit is what drives plant evapotranspiration. Dew point temperature is what we mechanical engineers like to look at to determine dehumidification potential and capabilities. And again, the wet bulb temperature is related to the potential to do evaporative cooling. So why do we care, right? Why is controlling humidity so important for our plants? Again, controlling humidity helps us to control plant evapotranspiration. And transpiration is critical to delivering water and nutrients from the roots to other parts of the plants. One of the biggest factors or diseases or deficiencies, I should say, associated with poor evapotranspiration is calcium allocation. And we see this pop up in almost all of our plants. I think I have 3 of them covered of the crops that are represented here today. Blossom end rot in tomatoes. This is a calcium deficiency frequently caused by evapotranspiration. Leaf tip burn, chlorosis around the tips of the leaves caused by transpiration rates that actually might be too high because the space is too dry and water can't pull calcium fast enough to the rapidly growing leaves. Calyx burn on the tips of the leaves on top of the strawberries, also caused a lot of times by poor humidity control. A lot of you I know are concerned about high humidity. So calcium allocation is actually frequently due to low humidity. to dry conditions. Pathogens, on the other hand, are typically associated with humid conditions, but that's not always the case. Powdery mildew actually likes dry air. So for those of you in cannabis and hemp and other crops who are concerned about powdery mildew and are asking for drier and drier room conditions, you might actually be facilitating the growth and distribution of powdery mildew spores. Botrytis, on the other hand, does like it humid. So having a drier condition could help you to prevent botrytis. So finding that balance, right, is really critical to the health of your crop. And controlling humidity ultimately helps to control growth and control water and fertilizer use. So in speaking of controlling growth, this study recently published showed that reducing the vapor pressure deficit actually increased the relative growth rate and net assimilation rate of tomato plants. And look, reducing the vapor pressure deficit significantly increased the fruit yield by almost between 20 and 25%. So again, those of you who are looking for, higher and higher VPDs, more dry conditions, might actually be causing less growth from your plant. Also, by controlling VPD, we can control water use. Basically, if we have really dry conditions, our plants are using more water, right, to transpire, and they get thirsty, just like we do. Whenever I go back to Tucson, I remember within 24 hours why I used to always carry a bottle of water with me everywhere I went as a PhD student, because it is bone dry there, right? Same with plants. If they're growing in a very dry condition, they need more water, right? Or they're going to ask for more water, and as long as you give it to them, they're going to be fine. If you don't, they're going to wilt. And so if we actually lower the vapor pressure deficit, give it a slightly higher relative humidity, you can actually increase your water use efficiency. So what is the right VPD, right? That's what everybody wants to know probably. And, we online on our website, we have a little calculator for cannabis, leafy greens, and tomatoes. Leafy greens and tomatoes, this is published research. We've just, put it together into charts like this. You can also calculate your vapor pressure deficit based on the temperature and relative humidity that you are growing at or targeting to see where you are on this chart. Every chart for each of these crops looks a little different. I will say with cannabis that, we're still trying to figure out what the ideal vapor pressure deficit is, but the way that I've kind of broken it out is by vegetative, flowering, and actually inducing a stress condition. So anyway, you guys can check out the website to see what it might be for these other crops, and go ahead and calculate what VPD you have at your facility. So where does humidity come from ultimately? Well, it comes from a few different sources. Plants in the soil or the growing media is the source of evapotranspiration. Evaporation from the surfaces and transpiration from the plants equals evapotranspiration. It also comes from the outside air. Those of you who might be trying to grow in Florida or Texas or Hawaii or Colombia or somewhere really humid know that the air is very humid, and maybe you don't want to introduce that into your greenhouse or your facility because you're just going to increase the humidity rather than letting some of it out. CO2 burners. People don't necessarily realize that the products of combustion of natural gas and air produce 3 different byproducts. They produce CO2, of course. They produce heat, but they also produce water vapor. So if you have a lot of CO2 burners in your facility, or you're using, say, a natural gas direct fired heater and you're not venting it out of the greenhouse because you want that CO2, you're also injecting water vapor into the greenhouse. And then there's foliar sprays, right? Some of you are spraying maybe weekly the leaves with different, maybe it's with fertilizers, maybe it's with pesticides, but that increases the humidity inside the space very rapidly and for a short period of time. There's also people. We also, when we're sweating, working real hard in a greenhouse, we're generating water vapor as well. All right. So how do we control humidity? Okay, I'm going to break this into two pieces. There's dehumidification, which I'm guessing most of you, that would have been a great poll question. I'm guessing most of you are here to learn about. But there's also humidification. Remember, there is value in having a lower vapor pressure deficit in a more humid environment. And if you are in Tucson, if you are in Michigan and it's winter and it's cold and dry outside, what do you do to add moisture to the air? Okay, I'm going to try and go through this very quickly. There's a lot of equipment, a lot of systems, a lot of strategies. And it's hard to cover them all. I'm going to do my best. Again, you know, if you have questions later about anything that I'm talking about, please hit me up for that. Okay, dehumidification. We are removing moisture from the grow space, okay? Best applications when we're recirculating the room air and we're not bringing any dry, fresh air from the outside. Greenhouses at night. When it is cold and dry outside, we can relieve some of that moisture. And of course, if you're in a humid climate, okay, and we want to remove moisture. Okay, so there's a few different strategies, whether you're in a greenhouse or what I'm going to call a warehouse type environment. We can ventilate, okay? That's the simplest thing to do, lowest energy, lowest cost strategy. And what we're doing is we're introducing dry air from the outside and exhausting humid air from the inside. Okay, we're exchanging air. We can heat, okay? Now, heating actually, if we just heat, let's say we just use hydronic heating with bench heating, then all we're doing is we're raising the temperature and lowering the relative humidity and vapor pressure deficit, but we're not actually removing any moisture, okay? But if we do use the air from inside for combustion and eliminate those byproducts, including water vapor, to outside the greenhouse, or even the warehouse, I guess, for that matter, then we can actually reduce the water vapor content of the air. We can also do both of these things at the same time. We can heat and we can vent. We can also, of course, air condition. Just by the process of air conditioning and cooling the air, we can condense water out of that air and we get some dehumidification. And then, of course, we can install dedicated dehumidification equipment. Okay, so ventilation, basically it equals outside air. Ventilation does not mean air movement, it means outside air, okay? And again, we're exchanging indoor air with outdoor air, we're removing heat and moisture, and there's energy savings potential, okay? How much we ventilate and whether or not we ventilate depends on a couple of things. One, what is the outside climate relative to the inside climate? And what other heating and cooling equipment do we have available? For a greenhouse, there's two typical ways that we would ventilate. We would use mechanical ventilation, AKA fans, or natural ventilation, AKA windows, right? Or ridge vents. Mechanical ventilation has the advantage of being predictable, consistent, controllable, right? Natural ventilation, we are at the whim of Mother Nature, okay? It's very weather dependent. It's also structure dependent, okay? So depending on the orientation of your greenhouse, depending on the location of the vents, will facilitate or even inhibit airflow coming in and out of your greenhouse. And it also can be very crop dependent. If you have very tall crops, they act like big obstructions to airflow. But if you have low-lying bed crops like lettuce, then that air can more freely move through the greenhouse, okay? For a warehouse type of situation, we can also ventilate. And I know a lot of indoor growers are concerned about ventilation for a few reasons, right? One is they're afraid of introducing bad things into their environment, right? Whether it's pests or pesticides or pollen or something else from another farm. They're concerned about leaking out carbon dioxide. And if you're in cannabis, you might be concerned about odor control. But you can ventilate, especially if the outside climate is good to do so. But we really only want to do it. This is the trick. We only want to do it when the humidity content, the humidity ratio of the air outside is less than inside. If we introduce outside air that is more humid than what we are controlling to inside, then we're actually going to increase the humidity content of the air inside, defeating ourselves. Okay, so typically you would see, economizers, which are basically, if you have an air conditioning system and you have a damper that you can open to the outside and relieve the air from the inside simultaneously, that's what's considered an economizer, as opposed to just recirculating the indoor air. There's also some sophisticated controls out there where you can actually determine what the mixture of outside air and recirculated air could be to maybe take advantage of the dry air outside. Even if it's hot outside, okay, now we still need to cool the air, but we don't have to cool it so much that we also have to dehumidify. And we're going to talk about dehumidification being incredibly energy intensive. So we had a little project in Maine where we were looking at heating and ventilating a greenhouse. And we plotted this chart that looked at ventilation versus the outside air dew point temperature. Inside, we were trying to control to 83 degrees and 70% relative humidity. That's awesome. I wish all my growers would want this vapor pressure deficit. And this equated to a dew point temperature of 72 degrees. On this chart, that would be over here, okay? So what you see, and maybe, this isn't surprising, but as you increase the outside air dew point temperature, we have to use more and more and more and exponentially more air to remove moisture, right? I mean, once it's 72 degrees outside, we're just introducing the same quality of air that's inside. So there is a point, down to 20 degrees. Okay, we don't need that much air, 2,000 CFM for, this 3,000 square foot greenhouse to control humidity. As it gets up to 50 degrees, it's still just 3,000 CFM. That's not too bad. But beyond that, right, it gets harder and harder to use ventilation for humidity control. I mentioned already we can use overhead gas-fired unit heaters and use that inside air for combustion as opposed to bringing in outside air for combustion, and then relieving that water vapor and the other byproducts to the outside through a flue. We would and then infiltrate, and then what would happen is that air that was used for combustion would then suck some air also from the outside through infiltration, which we would hope would be drier than what's inside. And that's partly why we would need the heating, especially if it was 20 degrees outside. So what if we vent and heat, right? What is the cost associated with that? So we looked at just heating. And then we looked at this question of, okay, we're going to use carbon dioxide, right? We want to enrich the greenhouse with CO2. Well, the cost of heating actually went down up to a dew point temperature of 50 degrees. Okay, because obviously it's colder, so you need more heat. It's warming up, you need less. But now, remember, this ventilation curve got really steep over here. And so now we need more and more heat to manage the temperature. And then if you add CO2 to this equation, it also goes up with ventilation as we would expect. All of this depends obviously on the cost of those resources at your location, but we would expect the curve to be generally the same. Okay, what about just dedicated dehumidification equipment? There's two basic types. There's the refrigerant-based and there's desiccant-based, okay? And some of you are familiar with both. For greenhouse, most of the dehumidification equipment that's out there is rejecting the heat that's generated by these machines back into the greenhouse. So again, this works really well if you're in Ohio or upstate New York or somewhere cold, right? Where you can actually take advantage of the heat of rejection because you need the heat anyway, but you can also dehumidify simultaneously with either a liquid desiccant-based system like this one is, or a compressor refrigerant-based system like this one is, and you get the benefits of both, but you would only use this at night or when it's cold, colder than what you want it to be. There are some new technologies that are coming online, like this one that's also using liquid desiccant that rejects that heat to the outside using cooling towers and chillers. You can also use chilled water to do this or refrigerant to do this, and but the key is you have to reject the heat outside, so you're only doing dehumidification, say in the summer when it's hot and humid inside. Indoor dehumidifiers, I'm sure most of you are familiar with a lot of these technologies, right? We can hang them from the rafters, and they can be large or they can be small. We also have these little roll-in dehumidifiers that we can use in a pinch or temporarily, and we don't need a permanent installation. And most of these are compressor based, but there are some desiccant based systems. Based on our analysis, desiccant probably only pencils out when you need a really cold and dry condition. But most of these compressor systems are actually, I'm going to say, relatively efficient, down to about 65 degrees. I'm going to get to that also in a minute. Air conditioning, okay, as a method of dehumidification. Those of you who, drive around in your car in, cold environment, and the windows fog up on the inside. And now new cars, I've noticed actually, when you put on the defrost setting on your car for heating, have any of you noticed that the air conditioner light turns on? And the reason that's happening, so what's happening is that the air conditioner is being activated to condense out the moisture that's being recirculated from your car. And then there's a heater after that reheats that air before it gets delivered through the vents in your dashboard. And so air conditioning by itself, we're creating these very cold coils with refrigerant or chilled water. And as long as the surface of these coils is less than that dew point temperature, we are going to condense water out of the air. And that's what air conditioning is basically doing. It's cooling and dehumidifying simultaneously. Okay, we can air condition a greenhouse. I don't usually recommend it. It's insanely energy intensive, and we want a very well sealed greenhouse if we can. Not this, with this vent up here, if we can help it. Maybe this is a day that they don't need air conditioning, so it's a hybrid greenhouse, so I approve that strategy. But we can air condition a greenhouse, and there's a lot of different ways, right? These are smaller greenhouses, so we have smaller systems. This is a very large greenhouse, so we have these large package units with all this ducting being delivering positive pressure air to the greenhouse. The reason it's energy intensive is because essentially we are air conditioning the sun. If we are using these systems for dehumidification on a hot, humid, sunny day, not only are we trying to remove moisture, but we are also trying to remove the solar heat gain that is coming in to the greenhouse to light up our plants. Okay, if you're in a building, right? I mean, again, a lot of different ways that we can apply air conditioning to the greenhouse. We have rooftop units, we have ground mounted units, with condensers, we have these wall mounted guys. I mean, there's a lot of different ways we can do it. And I'm going to talk more on the pros and cons of that. And what to look out for. Then there's desiccant-based dehumidification. Desiccant works really well when compressor or refrigerant-based systems don't. Again, that's when it's really cold or really dry that you're trying to get. And basically, you know, desiccant is like kitty litter. This would have been a great poll question, because I always ask this when I give a live presentation, is how many of you have a cat? Raise your hand if you have a cat. Okay, it's about 20%, I'm gonna guess. So those of you who have a cat know how heavy kitty litter is. Oh my God, it's like the heaviest thing in the world. Well, now imagine having a wheel filled with kitty litter. These things are heavy, and they have gigantic motors to rotate this heaviness. And basically, right, this desiccant sucks the moisture up like your kitty litter would suck the urine up, right? Excuse me, we're getting gross. And then we reject that moisture by heating you know, a portion of this wheel as it rotates. So it's rotating in one direction and picking up the moist air from the room, and then it continues to rotate, and then we blow hot air over it to recharge that desiccant, and then we might then blow cool air over another section of this desiccant so that we're not adding heat back to the room. It's a process, and these equipment are big. And one of the things that we have to figure out if we use these systems is, where do we reject that hot, moist air out of the building? It's not so easy to place this outside like it would be an air conditioning system. Okay, humidification. All right, we're adding moisture to the grow space, right? Best applications if we have dry climates, clone rooms for those of you cannabis growers, also anyone who's, you know, doing grafting or working with plants that don't have root systems yet. We tend to want a more humid environment in there. And I'm going to say over dehumidification. Some of the air conditioning equipment that's out there now doesn't have variable speed controls on some of their compressors or their fans or whatever. And so they've only been looking at, okay, we need to hit all this dehumidification when the lights are on and the plants are pumping. And then what happens? Then the lights turn off and we still need some dehumidification because your plants are still breathing. And now that system can't turn down, and we over dehumidify the space, or we over dehumidify the space when we first transplant young plants from another room that, you know, had a less intense environment, and they're just not pumping the water yet. And now, you know, we're creating a very dry condition. This picture in the bottom right, by the way, is what one of my clients did to overcome that over dehumidification. They actually put in a big evaporative cooler in their grow room. Not ideal. Bonus question at the end, if anyone can identify this person helping me with my research back at U of A. Okay, so in a greenhouse, we humidify in several ways, right? Evaporative cooling, high pressure fog. Some of us hose down the floors. That's actually what we did on that mushroom farm that I worked on as an undergrad. We couldn't keep the space humid enough for growing mushrooms, and we were hosing down the floors every couple of hours. You can also close the vents, right? And just trap all that moisture. The problem is then you're trapping all that heat too if it's a sunny day and you don't want it. With a warehouse, we tend to do things a little bit smaller scale or a little bit more gently, I would say, using ultrasonic humidifiers, steam humidifiers that can even be placed in the air handling, air conditioning equipment. And some people do use high pressure fog, say in their clone rooms. So why the heck is it so hard to control humidity? Okay, so the things that are in bold are the things I'm going to go into here for a few minutes. But one reason is we underestimate evapotranspiration, or we overestimate it, I would say, even. You know, a lot of people forget that when you irrigate a plant with, say, 1 gallon per plant per day, that there's, you know, 30 to 40% drainage of that water. And so now we've sized a system that's maybe 2 times what it needed to be. The climate is too humid or too dry, making it hard to use ventilation. We use recirculating air, which, you know, if we don't have proper dehumidification, the moisture just builds and builds and builds and builds until it starts raining inside our grow facility. The conditions are always changing, inside and outside, right? We have these transition periods between light and dark. Plants are dynamic and they're growing and changing. That's really hard for HVAC equipment to respond to. And I would say that we just haven't gotten to the point where we can dial in HVAC to respond to those incremental changes. And that comes down to equipment performance, and where sort of the deficiencies are there. And it's incredibly energy intensive. I've mentioned that a few times. And just overall, we have a lack of understanding and communication between HVAC professionals, manufacturers, growers, researchers, right? We need to do a better job at communicating. So in terms of equipment performance, most commercial air conditioning equipment is designed for cooling, not dehumidification. So you're humming along, the lights are on, you're like, oh yeah, you know, like we're able to control humidity and temperature and things are going well. And then the lights turn off. Well, there's no heat gain to the room. So your thermostat's like, hey, I'm cool, right? Literally, I'm cool. I don't need to do any work. And your air conditioner turns off and it's like, I don't need to work because the temperature is fine. And you're like, oh no, what just happened? Why is my humidity spiking at night? Because your air conditioner turned off, right? So right here, we see the air conditioner turns off when the lights go out. The temperature is going down because there's no heat gain to the room, but the relative humidity is going up. It's going up for two reasons. One, because the temperature is lower and it's relative humidity. And two, because the moisture content of the air is also increasing as your plants continue to breathe. This dynamic and transitional environment that we have also affect, you know, our air conditioning equipment, depending on how it's sized and where it's located, can't keep up with the rapid change that we have. Lights turn on. Okay, here I go. I'm gonna condense some water. And then it finally, okay, I got a steady state. And then the lights turn off and you checkerboarded and you're gonna turn it off, you know, sort of gradually. It didn't even respond to that, basically. Not until all the lights are off. It's like, oh, okay, I can turn myself off. And it takes, look at how long it takes for the air conditioner to respond to reducing the amount of moisture in that space. Oh, my little hour things are a little messed up. Anyway, HVAC equipment isn't super fast at responding to changes in our environment. And here's a big one. Moisture removal capacity varies based on your equipment type and your room conditions. Warning, manufacturers report the moisture removal capacity at standard rated conditions. And these standard rated conditions are 80 degrees and 60%. So anytime you Google a dehumidification piece of equipment, or you ask for a cut sheet from a manufacturer and it says we remove 205 pints per day, that number is based on these conditions, 80-60. But I don't know anyone who is growing or targeting these conditions. If you're in a vertical farm, you're somewhere between 65 and 72 degrees and 50 to 60% humidity. If you're drying cannabis, you're like down around 60 degrees and 50 to 60% relative humidity. And the moisture removal capacity of that equipment drops very quickly with different temperatures and different humidities. If you're in a vertical farm, you're kind of in this range, right? For this unit specifically, it has a capacity at this 80-60 up here, right, of 9 pounds per hour. You're like, oh, I need to remove, 18 pounds per hour. I need 2 units. No, you don't. You need 3 because you're actually growing at 70 degrees and 60%. Or, no, you don't. You need 4 because you're growing at 70 and 40% relative humidity. God, I really hope none of you are growing at that condition. And if you're in a drying room, it's even worse, right? Look at this. You don't need 1 up here. You need, what is that? 2 at least, maybe 3. Did I do that math right? 393. Yeah. And that's why a lot of you are having trouble with humidity control, even with dehumidification equipment dedicated to your facility, because you are assuming, as you know, and nobody told you that, what the equipment says it's going to do on their product sheet is what it's going to do, when in fact it's going to do half or a quarter of that actual rated capacity. And so you actually needed more of their equipment. Energy, just real quickly, regardless of how you split it, some people say, oh, desiccant dehumidification is going to be more energy efficient than using an air conditioning. Well, not necessarily. With air conditioning, right, and chilled water, we have very cold air, okay, less than 50 degrees. A lot of times less than 45 degrees to hit that dew point temperature and condense water. Well, we don't want to deliver super cold air to our plants, right? We don't want to deliver 50 or 45 degree air to our plants. So what do? We reheat. So we're air conditioning and then we're heating. That's a lot of energy. Desiccant. Well, we have to recharge that desiccant with really hot air, at least 120 degrees. Well, now we don't want to deliver 120 degrees to our plants. So what do? We cool it. So now we're heating and then we're cooling, right? I mean, it's just we've swapped positions almost. What are other humidity control strategies that you can implement rather than some of these things if that's not going to work for you? One thing you can do is you can, instead of having, soil-based grow systems or a ground soil for, ground cover for your floor, you could use, replace it with a concrete floor, which isn't going to evaporate water, though be careful about reflection of light. You can switch to hydroponics or other growing methods other than soil where you aren't evaporating a lot of moisture from the surfaces. That's the goal here. You can also increase air movement. I'm going to come back to that. And if you're in, an indoor farm, in a warehouse, insulate your walls with a vapor barrier to prevent moisture from coming in through the structure, but also to control what's leaving. I've had debates with other engineers. Maybe in a humid climate, we want the walls to be a little bit leaky or permeable, I should say, to water vapor. The problem with that is, one, the outside condition and inside condition is changing all the time. So how do you really control the rate of moisture, transferring to the other side? And a lot of times those materials are susceptible to mold growth. So we don't want that too. So I want to talk about air movement for a second, because I think that this is a strategy that's often missed, especially by greenhouse growers. And there's a lot of research. I'm sorry, I didn't have time to put this all together, or a bunch of research articles together, but there is a lot of research that shows that just by moving air across your plants, especially with those leafy greens, that you can prevent a lot of those issues associated with evapotranspiration deficiencies. And so, air movement is really key because it removes the waste products from your plant, including water vapor and including heat from, say, lamps in a vertical farm, right? As well as that oxygen that they're producing. Thank you very much. And it also helps to deliver the dry air from wherever we're introducing it into the space to the leaf, as well as carbon dioxide we might be enriching in that space. And ultimately, it helps to break up the boundary layer. There's like this little pocket of air that will form over your leaf where that water vapor will get trapped, or that water will get trapped that's coming out of the stomata. And by blowing air over it, we break up that boundary layer and make it more possible for that water vapor to be released away from the plants. And it also helps to discourage pests. I have lots of pictures of different air distribution schemes. This is just a quick sample. We have fabric ducts In this case, it's combined with horizontal airflow fans. You know, I mean, ducting is a good way to deliver air, and we can be really strategic about the diffusers we select, about the locations of those diffusers in generating air movement over your plants. Fabric ducts are nice because, you know, you can actually work with the manufacturers and they will engineer the holes and the nozzles so that you get exactly the air velocity that you want across and through your plant canopy. If you're in a vertical farm, a lot of you, I mean, this is a very small version, but a lot of you are using fans like this hanging from the racks to maintain the momentum of air across the plants. You know, greenhouses, you see horizontal airflow fans a lot. That's really good for mixing air, especially in a heating condition, so you don't get, you know, stagnant pockets of air. You see air tubes below benches, above, like this. You know, Cornell recently did a study. I know that folks at Chiba University 20 years ago did a similar study showing that blowing air down vertically into the plant canopy, especially with leafy greens, helps to push air down into the center of the plants, preventing a lot of that leaf tip burn issues that you see with improper evapotranspiration and humidity control. All right, that's it. And I knew it was going to be long. I know there's 5 to 10 minutes for questions. And yeah, I'm excited to hear from all of you.
Great, thanks, Nadia. Great presentation, absolutely excellent. So if you can stay, Nadia, let's see if we can answer all the questions. Even if we go a little bit past by 3, we are recording this webinar.
Okay.
So if we can get all the questions answered, will be recorded so people can take a look later. We have a few questions here, I think we can do in time. So first of all, 2 people raised their hands when you ask if they have cats. I think more people have cats, but just 2 people raise their hands here, just so as you know. I'm seeing here one thing that people is asking, we can do this quickly out of the way. Is the presentation slide deck going to be made available? Would you be willing to share this presentation? We have the video, or they can get in touch with you. I think would be this email in the screen is a good one to reach out to you for the presentation.
Yes, that'd be great.
Okay, so everyone, if you want to get the presentation, get in touch with Dr. Nadia. Her email is on the screen. First question here, and I think you answered this throughout the presentation. Is ventilation absolutely necessary?
So I would say ventilation, as in the introduction of outside air, is not absolutely necessary. However, there are a few good reasons to do it. In addition to, you know, humidity control, potentially. There's energy savings associated with it because you're only using fans as opposed to, say, compressors for air conditioning. So that is huge. Another reason is that if you don't have CO2 enrichment, ventilation can actually be a source of carbon dioxide for your plants. I've worked with growers who had a sealed indoor farm and couldn't figure out why their plants weren't growing. And honestly, I couldn't either until I asked the question, well, you guys are enriching with CO2, right? And they said no. And I was like, oh, well, that might be the issue. So even having that as a stopgap in case you run out of CO2 or your CO2 system fails is good to have. And the third reason is code requirements. There's a lot of jurisdictions out there that are starting to require folks to meet minimum ventilation requirements for as an F1 building, a factory type of building. So no, it's not absolutely necessary. It could be by code depending on where you are, and it's just not a bad idea to have available.
Great. Second question, influence of site elevation. So the site elevation plays a big role in controlling humidity in greenhouses. I think with all these factors together, outside air, ventilation, and all these methods.
Right. So the influence of site elevation is kind of the same idea of it depends on your climate. We know that at higher elevations, it tends to be cooler. and then at lower elevations. And because cold air can hold less moisture, even if it's say 80% relative humidity, but it's 40 degrees, that could still be less moisture than what's inside at 80 degrees and 70% relative humidity. So having actually a higher elevation could be an advantage in terms of humidity control. That is, unless you're at the top of a rainforest, then maybe that's a disadvantage. So it all goes to what is the microclimate around your specific site.
Perfect. The next one, it's related to one of the pictures that you show. So they're saying here, hanging HVAC equipment from rafters. When anything goes wrong, it ends up on product. Please provide a better scenario or mitigation. So are there any alternatives to that?
Yes, thank you, Ed, for that question. So I'm a big fan of having as much equipment outside the production room as possible. When I have it my way, the only HVAC equipment that you would see inside a room would be the ducts and or diffusers, and maybe some fans. But Ed is absolutely right that like those dehumidifiers that I showed hanging from the rafters, they are dehumidifying. They're removing moisture, and that means that there's condensate. And if that condensate is not properly plumbed, or if the plumbing gets clogged, then that water is going to find the path of least resistance, which is going to be on top of your plants down below. And the other thing, and that's obviously not a good scenario. The other thing is that, if you need to maintain that equipment, and it's above, your crop, or even in the room with your crop, that you could be disrupting operations. How are you going to get a ladder between your plants and, the ceiling to work on that equipment without, causing damage to your plants? So, yeah, anything we can do to keep that HVAC equipment outside of the room and use ducting to deliver, to remove the air and deliver, conditioned air is always a benefit, in my opinion.
Perfect. I'm gonna jump to another person question. We go back. Ed has some other good questions as well. Just chance for other people, and we go back these in a second. So another one is edema due to humidity or other factors? How to reduce edema incidents?
Ooh, that is a good question. I don't know. I don't have a good answer for that question. My guess is that it can be caused by transpiration. Oh man, I can't remember. Let me get back to you. And maybe somebody else has an answer to that question.
Perfect. We can get back to that. That might be a good follow-up topic. We can come up with something, follow up by email. Great. Well, thanks for the question. That was a good question. Yeah, that was a good question. All right. So another one is, how might I regulate humidity in a tropical plant greenhouse crop using water temperature modification, especially using an aquaponics system with tilapia or arowana?
Yeah, so tropical environments are definitely a challenge for humidity control. And, first I would want to look at the weather to see if the moisture content of the outside air really is higher than what it is inside. I would imagine in a tropical climate, it would be, probably the best scenario is when I said, other strategies other than dehumidification include air movement, and having really good air movement over your plants and through your plant canopy to really break up those pockets of air and move that moisture that the plants are generating is actually very effective at keeping your plants healthy. And that's why I said it's kind of, air movement is kind of an unsung hero. We've all become very obsessed with removing moisture, when really, you know, from the entire space, but really what we want to do is remove moisture from around the plant. So if we can push that moist air away from the plant, then we can actually, you know, grow very healthy plants.
Perfect. We got one follow-up here. So Dr. Neil Madsen from Cornell University contributed for the question that we just had on the edema. So edema seems to be related to at least two environmental factors: lack of UV and blue light, and as well as also more prominent in high humidity. So yeah, lack of UV blue light and prominent in high humidity conditions. Thanks, Neil, for participating. One more question here. So follow up on our list. Nadia, thank you so much for your presentation. With traditional wet wall greenhouses, linear airflow model towards the extractor fans leads to significant microclimate gradient across the greenhouse. Any recommendations on addressing this without going full hybrid greenhouse?
Yes, you're right. There can be a large gradient of temperature and humidity from one end of the greenhouse to the other. Where did that question go? It disappeared.
Sorry, I answered, but
can you put it back?
Quick answer questions.
Answer is under answer.
Okay,
here we go. Got it.
Towards the end, yeah.
Right. So, yes, there are actually a couple of things that we can do. One is using fans inside the greenhouse to help to mix that air up, though I will admit that the velocity and volume of those extraction fans is a lot higher than, say, those little HAF fans that we might put in a greenhouse, so it might be hard to overcome that momentum. There are some creative ways to positively pressurize a greenhouse with an evaporative cooling pad. So, you know, having almost like a chamber at the entry of the greenhouse where you have a wet wall, and then that cool, you know, humidified air fills the chamber, and then we could have fans then blow that cool humidified air into the greenhouse through convection tubes or fabric ducts to positively pressurize the greenhouse. In that case, we would want to find a way to relieve that air. I've seen greenhouses that look like balloons that are inflated because they positively pressurized the greenhouse but didn't think about how they were then going to relieve all that outside air that they're delivering into the space. So I imagine they might fly away someday. But yes, there are creative ways we can create a positive pressure greenhouse using a wet wall simple system.
Perfect. Nadia, questions do not stop coming. So I think what we can do, let's take two more questions. Awesome. Let's take two more questions, and then what we can do, maybe you and we can write up all these other questions, and I can follow up with everyone on the newsletter, or just send an email to the attendees list with some quick answers here. Otherwise, we're going to be here for a long time. So let's get two more questions, and then we can wrap up. The next one is, how effective would infrared heating be for reducing overnight humidity, since leaves in line of sight would be warmer and less prone to leaf wetness? That's a good question.
All right. So did you leave that one open for me? Where is that one?
Yeah, this one is there. 1, 2, 3 is the third question.
Third question. Yes. So so infrared heating doesn't do really anything to reduce the moisture content of the air. However, adding that heat to the air does, you know, reduce the relative humidity by increasing the temperature. It is tricky. I mean, the bottom, you know, the second line on your question is really the key. is that one of the challenges with infrared heating is that not all surfaces get exposed or exposed uniformly to the infrared lamp that's, you know, creating that infrared light. Yes, those leaves would be warmer, definitely, and therefore would be more prone to transpire or to evaporate the water down there near the leaf. I would just say that, you know, okay, so that evaporation happens, we still want some air movement to then, you know, take away that moisture that is being generated by the plant. I think that's a really interesting concept, actually. But again, you know, it's really the tops of the plants that are going to get the benefit of that infrared heat, which is, you know, where most of the growth is occurring, depending on which crop you're growing, but doesn't really help the leaves down below. And so moisture can still get trapped within the canopy. I like that question.
Might be worth having a slide about that, Nadia, for the next presentation. That's pretty interesting.
Yep.
Perfect. So let's get the last one, and then we can answer the other ones offline later on. So the next one, pretty applied. What is the best sensor we can use to measure air humidity in a greenhouse?
So I did not touch on sensors. Relative humidity sensors, any sensor that is measuring moisture content of the air is notoriously unreliable, unpredictable, and fails frequently. As soon as it gets really wet, it dies, basically. And it's really hard to keep them in calibration. And it's definitely one of the bigger challenges, even in, you know, commercial HVAC systems where we want to monitor both humidity and temperature of inside and outside air, is that, okay, the temperature sensor can work, you know, for years and years and years without thinking about it, but that humidity sensor drifts very quickly. And so, I mean, if you can, you know, the best one is probably, you know, the sling psychrometer that you use, you know, with your hand and sling it over your head to measure the humidity content. Those are pretty reliable. But in addition to that, other types of humidity sensors, I would just say that you want to make sure that you're calibrating them at least every year, that they are protected so that they don't get a lot of dust on them, that they don't get wet inadvertently from, you know, those foliar sprays or from irrigation or high pressure fog systems, because anything that really accumulates on that sensor is going to cause it to read, you know, an unreal value. I mean, I wish we had good sensors. If somebody on this call is a manufacturer of humidity sensors and thinks they have a good one, I would love to talk.
That's great feedback. Well, everyone, I hate to do that. There is nothing better than an engaging discussion afterwards. We still have 10 questions to go. So we still have 10 unanswered questions. But we are already 11 minutes past our deadline here. I don't want to keep people online more than we should. Nadia, thank you so much for the presentation. As you can see, it generated a lot of interest. We still have 74 people on the line. So most of the people stay all the way to the end with us. That's very nice. So I'd like to thank Nadia for the presentation. Thanks everyone for joining, and let you know that our next webinar is scheduled for October 25th at 12 at noon. And we're going to be talking about strawberry and tomato responses to light and CO2 control. This next webinar will be presented by Dr. Neil Matson at Cornell University and Jonathan Allred. He was a PhD candidate. Oh, there you go. He's a PhD candidate at Cornell University. There you go. You can register for the next webinar on our website. I'll send a follow-up email, so please join us for the next one. Nadia, if you can, I would suggest let's take a look on those questions here offline, and maybe you can provide just a short answer to all of those. We don't have to expand much, but just give them some directions, and I can follow up with everyone on that, send an email. Thanks again, Nadia. Any final marks, any final comments?
No, thank you for hosting this and for having me, and thank you to everybody who attended. And if you have any follow-up questions, please feel free to contact me directly, and I'd love to engage in a conversation with you.
Wonderful. We still have questions coming up to this last minute, so that's a good news. Thank you so much, Nadia. Thanks, everyone. Have a good day. Bye-bye.
Thanks, everyone.